Hopefully nobody is keeping count, but I think this is enzyme cheesy demo number 3. Say that this is our enzyme and the particular substrate of this enzyme is this substrate. And what you can see is that the two just really don't bind. And in fact, this enzyme alone will have no activity. We actually call that an apoenzyme. So an enzyme that needs a cofactor in order to bind its substrate is non-functional. It's called an apoenzyme. And it's only when this apoenzyme gets its cofactor that it becomes whole and can bind its substrate. We call it a holoenzyme. So an enzyme plus its cofactor is a holoenzyme. So hopefully that cheesy demo allowed you to better visualize what the difference is between an apoenzyme lacking its cofactor, a holoenzyme having its cofactor, and the cofactor being absolutely essential for binding to the substrate. So recognition of the nature of cofactors being variable. Some of these cofactors are essential ions. Some of them are coenzymes that are vitamin derived. Let's go ahead and write down some of the categorization of cofactors, with cofactors being the large umbrella term. If you're ever in a sexy-minded discussion with one of your professors and you can't remember whether it's an essential ion or it's a coenzyme, just say cofactor because you're safe. That's the umbrella term that describes all types. But if we split them down into their subtypes, essential ions are a very common type. These are typically positively charged metal ions. For example, a zinc 2+ cation is really common at the active site of an enzyme. And momentarily, we are going to look at my favorite enzyme, carbonic anhydrase, and look at the fact that it has a zinc cofactor, a zinc 2+ ion, that helps it in both binding of its substrate and also catalysis of the reaction, which was likely for our cheesy demo as well. Coenzymes are typically vitamin derived, and they often play a role in something called group transfer. We've actually talked about that already. Remember talking about transferases, where they're actually moving a group from one place to another. This can be multifaceted, and we'll talk more about what are some of the things that a coenzyme might transfer, because sometimes it's as simple as it's the taxi cab for carrying electrons from one place to another. Let's begin our search for better understanding of cofactors with the essential ions. So let's take a look at the two categories of those enzymes that have metal ions associated, or at least require metal ions to be in some way involved in the reaction. And what's crazy about this is that more than 1/4 of all enzymes require metallic cations in order to reach their full potential. So we all have things like that in the world that we need in order to reach our full potential. For these enzymes, they have to have some sort of metallic cation involved in order to reach their full catalytic activity. And we can split these down into two groups. There are metal-activated enzymes. Metal-activated enzymes sometimes are enzymes that don't directly bind to the metal ion, but instead, in some way, this metal ion is involved in the reaction. And I actually brought up a sweet example from the bioinorganic concepts involved in the determination of glucose, cholesterol, and triglycerides. I'm actually going to bring this over so that you can take a quick peek at it. This reaction mechanism is pretty sweet, but for our purposes, what I want to draw your attention to is that when this enzyme binds to the ATP substrate, it requires that ATP be chelated to or bound to the magnesium cation. And so the enzyme won't recognize the substrate unless there's a magnesium 2+ cation associated with the substrate. So this would be a good definition of a metal-activated enzyme. Kinases, such as this kinase, are commonly metal-activated. So we will often see ATP being bound to magnesium 2+ in order to allow the substrate to be recognizable. So in this case, we would define metal-activated enzymes broadly as either requiring added metal ion or being stimulated by that added metal ion. Kinases are a good example. Now, metal-activated enzymes are cool, don't get me wrong, but really even far cooler than metal-activated enzymes are metalloenzymes. This is the most beautiful thing in the world because it is the melding, the wonderful melding of inorganic chemistry and biology into bioinorganic chemistry. Because in order to understand metalloenzymes, you really have to understand the chemistry of the D metals, the transition metals, and the ways in which that impacts their ability to catalyze reactions at the active site of an enzyme. So metalloenzymes are defined as having a metal ion firmly bound at the active site. So rather than the metal activated enzymes where, remember the example we looked at, the magnesium ion wasn't in any way bound to the enzyme, it was actually bound to the substrate. Metalloenzymes have to have the enzyme firmly bound to the active site. You know, in our cheesy example, I mean, it's not very to scale if this were the case, but I mean, this could be a magnesium cation that without it, this enzyme can't bind to the substrate because maybe it is the cation that actually attracts the substrate and binds to it. Additionally, it may very well then play a catalytic role in allowing the enzyme substrate complex to become product. So there may be a catalytic role that is also determined by the cofactor, the metal ion in metalloenzymes. And as I mentioned, my very favorite enzyme, carbonic anhydrase, is a really wonderful example of this. When I was an undergrad, I had the incredible opportunity to work for a long time in a research lab. I worked with carbonic anhydrase, and I did something called electron paramagnetic resonance, or EPR, or sometimes called ESR. So this technique is used to look at unpaired spins, paramagnetic D metals. And so at the active site of carbonic anhydrase, there is a zinc 2+ cation that typically sits there. In a minute, we'll look at a picture. And what I was doing was I was actually taking a strong chelator called pidite and using this organic chelating compound to rip the zinc ion out of the active site of carbonic anhydrase. Cruel, you say. Well, it would cause the enzyme to lose activity entirely. But then what I did was really sweet. I would take a cobalt metal, the cobalt ion is a D7. It's a paramagnetic metal. And so it has unpaired spin, meaning AKA it's sweetly colored. It is purple. So once I replace that cobalt cation at the active site where the zinc cation had been, the enzyme turned from clear to purple. It was the most BA thing ever. So let's zoom in to the active site of carbonic anhydrase and look at the reaction mechanism that is made possible by not only the zinc cation, but guess what? Like, okay, if being a zinc metalloenzyme was not enough to make you love carbonic anhydrase, get this, it also has not 1, not 2, not 3, but 4 histidine residues at the active site. Let's see what goes down with those histidine.